Hello and welcome to the Flat Earth Preposterous Perspective. I wasn't planning on doing another Flat Earth video, but the flatheads perspective nonsense was just too easy for me to ignore. In this video, I'll be discussing how perspective works and, more importantly for flatheads, how it doesn't work. There will be math, there will be geometry, but I'll try to keep it as simple as possible because I know flatheads hate anything that requires them to think. First question: what is perspective? Perspective is simply the apparent reduction in size of an object as it recedes from the viewer. This effect is clearly visible in this photograph I took of Buckingham Palace. Notice how the horizontal lines appear to converge as they get further from the camera? That's perspective. Eventually, if the building was large enough, they would converge to a point. This is called the vanishing point. For this to occur, the building would need to be infinitely long, which obviously it isn't. Similarly, although less visibly, vertical lines are also converging. This is noticeable at the edges of the picture where the vertical edges of the building are not perfectly vertical in the photograph. If these were extended upward, they would eventually meet at their vanishing point. There is a simple equation that can be used to calculate an object's apparent size. The angle that an object takes up in your field of view is the inverse tangent of its size divided by its distance. To verify this equation, let's do some calculations based on this photograph. Specifically, I'll estimate the width of Buckingham Palace and then compare it with the actual value. There are a couple of unknowns that I'll need to work out. First, how tall is Buckingham Palace? I could look this up, but I'll calculate it instead based on the height of the guard standing in front of one of the corners. Second, how far away is the nearest corner and how far away is the farthest corner? Once these are calculated, the width will simply be the difference of the two. The first thing to estimate is the height of the building. The height of the guard standing in front of the corner near the entrance is 150 pixels, plus or minus 5 pixels. If we assume his height, including the tall fuzzy hat, to be between 7 and 7.5 feet, that would make the scale at that distance to be about 20.7 plus or minus 1.4 pixels per foot. At that distance, the height of Buckingham Palace is 1390 plus or minus 5 pixels. Dividing this by 20.7 plus or minus 1.4 pixels per foot gives a height of 67 plus or minus 5 feet. Next, I need to know how much of the field of view is taken up by the building at its near and far points. The lens I used for this photo has a 34-degree vertical field of view. The image is 3416 pixels high, so I have about 100 pixels per degree. At its nearest point, the building is 2670 plus or minus 5 pixels, giving an angle of 26.7 plus or minus 0.05 degrees. At its furthest point, the building is 840 plus or minus 5 pixels, giving an angle of 8.4 plus or minus 0.05 degrees. So putting this all together, since the angle that an object fills is the inverse tangent of its size over its distance, we can rearrange this and say the distance is the size divided by the tangent of the angle. Using this, we can say the distance to the nearest corner, d sub n, is the height of the building h divided by the tangent of the angle, theta sub n. Similarly, the distance to the far corner, d sub f, is h over tan theta sub f, and the width is just the difference of the two. Plugging in the numbers, the height of the building h is 67 plus or minus 5 feet, theta sub n is 26.7 plus or minus 0.05 degrees, and theta sub f is 8.4 plus or minus 0.05 degrees. So, the calculated width of Buckingham Palace is 321 plus or minus 46 feet. The actual width is about 350 feet, which, given the crudeness of some of my estimates, most notably in the estimate of the height of the guard, gives an approximation within the expected range. From this, we can conclude that the equation I provided is correct and gives an accurate representation of reality. Now that we have a reasonable understanding of how perspective works, let's have a look at the mess the flatheads have made of it. In the flat Earth model, the Sun somehow follows a circular path about 3,000 miles above the Earth. There are obviously countless problems with this hypothesis. For example, how does it stay up? What causes it to follow a circular path in defiance of Newton's first law of motion? If the Sun is always above the Earth, why is there sunrise and sunset? This third question is the one I will explore today. When asked to explain sunrise and sunset, flatheads will invariably invoke perspective as their explanation. This will generally include some vague, hand-wavy comments about things approaching the horizon as they get further away. I've never seen a single flathead even attempt to give a more detailed explanation of how their perspective would work. I suspect they don't because they can't. It simply doesn't work, but they just keep repeating it like some absurd mantra that they've learned because they are, of course, completely incapable of any critical thought. Well, I'm going to go into the details of why their perspective is complete bullshit. The first thing I'll need to do is explain where the sun is using their model. As I stated earlier, they say the sun is about 3,000 miles above the Earth. Actually, they've given a wide range of numbers, but 3,000 seems to be the one most bandied about. So, just to make the numbers work in their favor, I'll say it's only 2,000 miles above the Earth. This will give perspective the best chance of working for them. Next, I'll work out the horizontal distance, the point on the Earth over which the sun will be when it's at its furthest point from the observer. Flatheads generally seem content with the idea that the circumference of the equatorial disk on their flat Earth is the same as the circumference of the equator on the spherical Earth. This is approximately 25,000 miles. So the radius on their equatorial disk is 25,000 over 2 pi, or approximately 4,000 miles, resulting in the radius of their flat Earth being double this, or about 8,000 miles. Exact numbers aren't too important for reasons that will be clear later. The sun will be at its furthest point from the North Pole during the winter solstice. This is about 23 degrees south of the equator, giving its distance as about 5,000 miles from the North Pole. The absolute furthest that a person can be from the sun is if he is at the South Pole, which flatheads think is fictional, at midnight during the winter solstice. The observer is 8,000 miles from the North Pole, the sun is 5,000 miles from the North Pole, so the observer is about 13,000 miles from the sun. If the sun is only 2,000 miles above the Earth, the angle that it makes with the horizon will simply be the inverse tangent of 2,000 divided by 13,000, or 8.75 degrees. So, at its furthest possible point, the sun will never be below about 8.75 degrees above the horizon. This is a large enough angle that the sun would never actually appear to be on the horizon. Remember my picture of Buckingham Palace? The far corner only filled 8.4 degrees, and it was quite visible. This, as I noted, is at its furthest possible point. Nighttime, however, happens all over the Earth, not just at its furthest point. Keeping this in mind, let's calculate how close the sun can be at midnight and not be visible. The sun will be nearest to the North Pole during the summer solstice. On this date, the furthest north you can be and still have the sun below the horizon at midnight is at the Arctic Circle. Let's attach some numbers to this. During the summer solstice, the sun is about 23 degrees north of the equator. This will make it about 3,000 miles from the North Pole. The Arctic Circle is about 23 degrees, or 1,000 miles, from the North Pole. So the horizontal distance from the observer to the sun is about 4,000 miles, and if we assume the sun is 2,000 miles above the Earth, the sun at midnight, while it's dark, will be about 26 degrees above the horizon. Some people might have difficulty with this simply being a number and say it doesn't really mean anything. They'll state, wrongly, that this will somehow depend upon the observer, which it won't. But just to shut them up, let me give a more visual explanation of the number. Imagine you're at the Arctic Circle at midnight during the summer solstice, and you're looking up at the sun because, according to the flatheads, that's the direction you'd be looking. Anything along your line of sight will block the sun. In order for something to be on your line of sight, according to the law of similar triangles that you learned in elementary school, it must satisfy the same 2,000 to 4,000 ratio as the sun. In other words, something 200 feet tall, say a 20-story building, that's 400 feet away, will be on the same line of sight as the sun. Yet somehow, according to flatheads, the perspective is so extreme that the sun will be on the horizon. One point that flatheads typically forget is that perspective isn't limited to nighttime. Consider this picture they took around 9:30 a.m. during the winter solstice. How far above the horizon should the sun be? First, let's consider where the sun would be using the spherical Earth model. In this diagram, up is perpendicular to the Sun-Earth plane, so, since this is the winter solstice, north is 23 degrees relative to this, and the equator is perpendicular to that. Toronto is 43.6 degrees north of the equator, so, since the angles must add up to 90 degrees, Toronto is 23.4 degrees from up. Since the horizon is tangent to the Earth, this means the sun will also be 23.4 degrees above the horizon. Unfortunately, it never occurred to me when I took this picture that I would be using it in this video, otherwise I would have taken it at noon, but it's still usable. Since sunrise was around 7:45 a.m., we can estimate how much lower in the sky the sun would be at 9:30 a.m. than it would be at noon. Sunrise is about 7:45 a.m., which is 4 hours and 15 minutes before noon. The photograph was taken 1 hour and 45 minutes after sunrise, or about 40% of the time until noon. If the sun followed a straight line in the sky, we could say the sun is at 40% of its maximum height, but since the sun follows a curved path, it'll be a little higher than this. For simplicity, I'll assume it's about 50% of its maximum height, or 11.7 degrees above the horizon. I know this could be calculated exactly, but an exact number isn't too important because the horizon is hidden behind buildings, making its exact position unclear. The lens I was using on my camera has a vertical field of view of approximately 47 degrees, so the distance between the horizon and the sun should be about 11.7 over 47, or about 25% of the height of the picture. As we can see, the spherical Earth model predicts the correct distance between the sun and the horizon. Now, let's see what the flat Earth model and its perspective predicts. In this diagram, the red line represents the distance from the North Pole to Toronto. The yellow line is the distance from the North Pole to the sun at 9:30 a.m., and the green line is the horizontal distance from Toronto to the sun. To find the length of the green line, the first thing we need to do is calculate the lengths of the other two lines. I've already established earlier in this video that the distance from the North Pole to the Tropic of Capricorn, the yellow line, is about 5,000 miles. Toronto's latitude is 42.6 degrees. For simplicity, I'll use 45. This decreases the distance to the North Pole, so it increases the length of the green line, which works to the benefit of the flatheads. More importantly, it would put Toronto exactly midway between the North Pole and the equator, and since that distance is 4,000 miles, the length of the red line is 2,000 miles. Since the photograph was taken 2.5 hours before noon, the angle between the lines is 15 degrees per hour times 2.5 hours, or 37.5 degrees. Now it's a simple matter of using the cosine rule to calculate the length of the green line. So, the horizontal distance to the sun is 3,624 miles. Since the sun is 2,000 miles above the supposedly flat Earth, its angle above the horizon would be 29 degrees. Since the field of view in this photograph is 47 degrees, the distance between the sun and the horizon will be 61% of the height of the photo. Clearly, the horizon is not below the nearest house. I would have rather drawn the line showing where the sun would be relative to the horizon, but it would be well above the top of the photograph. Now that I've thoroughly debunked the flathead's perspective nonsense, I should remind you that I used the height of the sun of 2,000 miles. The generally accepted height that the flatheads use is 3,000 miles. So, as bad as the results were for them, they would have been much worse if I'd used their accepted value. Next, let's look at what perspective actually looks like. In this photograph, the fact that the sun is in frame means that the parallel rays of light from the sun will be coming toward you through the clouds. As we all hopefully know, parallel lines coming toward you will appear to diverge, just like we see in this picture. Unfortunately, there's not enough information in the picture to make any useful calculations, but it's a pretty picture. Enjoy it for what it is. So, what did we learn today? We learned that the spherical Earth model makes accurate predictions of reality, and the flat Earth model doesn't. One could argue that the flat Earth model is idiotic, but that would be unfair. The model is just a thing. It can be neither intelligent nor stupid. I would be anthropomorphizing if I said the model was idiotic. Out of politeness, however, I won't say anything about the people who believe the flat Earth model because apparently calling idiots idiots is considered rude. Anyway, I hope you liked this video. If you did, hit that little like button. If you didn't, piss off. I'm still deciding on my next video. I've begun writing on wide-ranging topics like HARP, the Illuminati, Hollow Earth, Roswell, and others. So much bullshit, so little time. Until next time, remember, it's good to have an open mind, but not so open that the useful stuff falls out.